and welcome to the session. In today's session, we'll be discussing about some of the programs on the 8086 assembly language program, some programs on 8086 assembly language. Now, in the last session, we discussed about various issues related to 8086 microprocessor and discussed one or two simple programs on 8086 assembly. Now, in this session, we'll be taking up many more programs. Specifically, if you see, this is the content, is the reference material for this block is block 4 of MCS 012. We will be primarily covering unit 3 of this particular block, and most of the programs which we will be discussing, you can find reference to those programs in this particular unit 3 of block 4. We have already done around 7 sessions on MCS 012, and I'll request you that if you are watching this program as the first program related to MCS 012, then kindly go through those 7 programs, right? The slideshow which we are using today is also available in the download form from the that sources that is downloadable files which we have created for you. So you can always refer to sources help during this particular time, and there is a typical website and in fact the whole information is available in a file, so you can download that particular file and use the help. And over there, all these links, like all that is slideshow links are available, and you can download those slideshows from there and use them. So it is very important that you learn before you come to assembly language programming, because assembly language programming is not a very simple thing, right? Today what we are going to discuss, we will discuss about a quick review about 8086 processor, although we did a review of 8086 processor last time also, but for the sake of completeness, we will do some review in this particular session also. And then we will be doing discussion on various assembly program, primarily dealing with code conversion, decision making and looping. And all these things are very, very important. Why? Because what I told you last time also, and I'm repeating it this time, assembly programming is essential if you want to know about the details, inside details of machine, and you want to become confident about what you are dealing or what kind of programming you are dealing with. And this will definitely help you in high level programming in some sense. And finally, it also talks about the computer organization and architecture in some detail. So it is very nice idea to go through the assembly language programming. Okay, the 8086 microprocessor, as I told you last time, it was designed in 1976, but it is one of the fundamentally very important processor, and it has been since then it has been used. Its family is being, the family still is using the similar kind of concept. So therefore we are going through this particular processor. If you want to learn latest processors, this may be a good starting point, right? It basically consists of 64K segments. Now that's a very interesting situation. 64K segment, 64K means 64 into 1024 bytes, right? And the memory of 8086 microprocessor is byte addressable. So if we have 64 into 1024, 1024 is 2 to the power 10 directly, right? And 64 is 2 to the power 6. So roughly 6 plus 10, we have 2 to the power 16, right? So 64K segment means the instructions, we will be referring to any address into 64K bit segment only. Now if a particular segment which is there in the memory is 64K, the address size of that is going to be only 16 bits. That's what I want to highlight. That means any any memory address is going to be 16 bit. However, as last time we discussed that this particular microprocessor uses 20-bit addresses. So 4 bits from where it comes? They come from the segment register. Segment register is the starting location of the segment which is there in the memory, and that starting location we add one more hex digit, 4 digits we add towards the right hand side, you can say, okay, of that, I mean least significant area, we add the 4 bits or 1 hex digit. Both are the same. Okay, this particular processor can do processing of data of 8 as well as 16 bits. Technically it is a 16-bit microprocessor. Then the segment register, why? Because they point to the starting location of a segment, and then in the instruction the 64K offsets are there, so 16-bit is what we use in the instruction. Okay, and important register we discussed last time also. AX happens to be accumulator, BX base pointer, CX counter, DX it's just extra register for computation, but many a times used for multiplication, division, for those kinds of operations. And AH plus AL is, suppose AX is there, it consists of two 8 bits. AX is 16-bit, AH is higher byte of it, okay, and AL is the lower byte of it, both are 8 bits. Likewise, BX has BH and BL, CX has CH and CL, like that. Alright, and then pointer registers, they are just 16-bit, there are no decomposition of these pointers. Base pointer, source index, destination index, these are typical pointer registers which normally are used for processing, specifically for indexing kind of situation, index addressing modes kind of situation. Then we have instruction pointer which points to the instruction, stack pointer which points to the top of the stack, and then there are many flag registers such as carry flag, parity flag, zero flag, overflow flag, sign flag. Now flag is 1 bit, alright. So carry flag is primarily will be set if there is a carry out of whatever addition you are doing. Suppose you are doing 8-bit addition, then there will be carry out flag will be set as the, if there is a 9th bit which is coming out of it, carry flag which has to be set. 16-bit likewise. Alright, so carry flag is the carry carry bit will be stored in the carry flag. It can be either 1 or 0, no carry, right? Parity flag will be for parity generator, parity checking. Okay, so accordingly it will be set. Zero flag is a very interesting flag. Parity flag you won't be using very often, but zero flag you will be using quite often, because zero flags tells us, like if zero flag is 1, that simply means the register contains value 0, right? So that is what the last operation has resulted into the register content as 0. That's how we recognize it. All right, and overflow is also, I mean, all these flags are set by the last executing instruction. All right, so that is how they are recognized. Okay, sign flag, once again, sign bit is the leftmost bit, so sign flags are also used. So these flags, some of these flags we will be using, that's why we are, I wanted to remind you about these flags, and we will be discussing about some of the instructions which will be utilizing these flags, okay, especially looping and other kind of instruction. Instruction sets, very quickly, data transfer, suppose move, exchange, exchange two values and so on and so forth, add with carry, increment, multiplication, addition, ASCII adjust after addition, and decimal adjust after addition. We'll talk about DAA in one of the programs. Then bit manipulation, suppose you want to do bitwise operation NOT. So NOT is basically taking one's complement. Technically each bit will be complemented, and you know, AND operation you know, and the gate you know, right? This is AND operation, basically bitwise AND operator. Every bit is ANDed with another register's bits, like that. OR is also bitwise, XOR is also bitwise, shift left, shift right. They are very interesting operator, shifting the things to the left, shifting the things towards the right. So we'll use one of the shift rotation instruction. It is also shift instruction. Then transfer of control, basically call and return. Now call instruction we have not utilized in this particular presentation, but it is going to, we will be using some jump instruction which will be having different mnemonic as far as 8086 processor is concerned, and we will also use the loop instruction. Call and return instruction are primarily instruction for subroutine call or function call, which is a major part of your program. And many of you must have read this particular thing, that during the function call, stack is utilized, right? So there is one program which uses call and return, but that is part of unit 4, and I think you should go through that particular program. It is one of the most interesting program in the sense that how what kind of values are going to be put onto the stack, the return address and so on and so forth. All right, and then we have string instruction, which are typical to 8086, so we are not going to go into deeper detail into it because now they are not that important, although they were the ones which actually resulted into greater efficiency of string processing, for example comparing two strings, right? So these were the instruction. I mean, your compiler was not able to use these instructions, but these instruction, if you write using assembly program, you can utilize those instructions and your program used to be very, very efficient. And then finally the processing control, which basically required sometimes if you want to set carry bit, then you can do with the help of these instructions, and there were many or more instructions. Right now our programs won't be requiring it, so we have not gone into major details of this particular instruction. Now the final part is the addressing modes, right? So where my operand is, that is what I want to ascertain here. So let's look into the register. My operands AH and BH, right? So both the operands are in register. So move AH, BH simply says, move is the mnemonic for instruction, primarily which tells that there has to be a movement. This is the destination, this is the source. So the BH should be moved to AH register. Whatever is the content of BH register should be moved to AH register. Many a times I have been asked by the students, what will happen to the earlier content of AH register? It will be lost. It has already been, as soon as this instruction executes, the content of AH register will be overwritten. And that is why when you use call and return statement, you store some of the context of the register. In operating system, you will study about that particular concept. Context of the register means the content of the register will be saved and then later on will be restored from those saved location if you want to store if you want to save the previous content somewhere, right? So that's how it can be done. Now the second operand, the kind of addressing mode happens to be immediate. So this is a register operand, but this is an immediate operand within the instruction, right? So once you have fetched the instruction, your operand is within the instruction as part of the instruction, so it is readily available to you. AH still you need to fetch, I mean the set it is within the CPU, so no need to fetch from memory, but AH is there available for you and you can process these instructions very, very fast. Why? Because both the operands are readily available to you. Okay, similarly here also both the operands are in the registers. Whereas this instruction will move slightly slowly, which requires a direct memory reference. And one of the important things which you need to know is that in 8086, because of the restrictions on the number of bits which can be utilized by instructions, both the operands cannot be memory operands, right? I mean, just a simple example, one address is 16-bit, right? So two addresses, if we use both the memory operand, although this is not, right? But if we use, instead of AH, we use some another location, say Y, then 16 plus 16, already 32-bit has already been occupied, right? And the maximum length which we said was only 6 bytes, right? So other things were also there, so they discouraged this particular thing, and both the operands cannot be memory operands. This is one of the restrictions. Okay. And that is why we will be facing some of the problems which we face while writing assembly program. But they are not the problems. We should know that this is what the problem, this is how the instruction set has been implemented, and this is how I'll solve the problem, right? Or this is how what I need to do. Okay. So this is, I mean, remember, I'll be discussing it a little bit further also, but X is going to be a 16-bit address and X is a memory location. So X is a memory location in the sense a named memory location having a particular specific address. So X is the actually stating the address, 16-bit address of a memory location. All right. Then register indirect is when we bring in the address of a memory location as or whatever offset that particular memory location is into a register. So now this register becomes a pointer to the memory location in one sense. Okay, so it is a pointer to memory location. All these things happen in segment only, and this address is 16-bit, so BX will be storing only 16-bit. All right. So if I say indirect reference to BX, right, that means we are referring to whatever location BX contains, that is the address of the, or where, that is where our the memory that our operand is residing. So over here also in indirect memory address, we need to fetch the operand from the location which has been pointed to by BX register. So we got to fetch the operand. Okay, so in direct as well as indirect, we got to fetch the operand from the memory location. Same is the case. This is also register indirect, another example. So you can refer to this particular thing. Now it's very important. I think the part of the portion you won't be seeing towards the right. That's what the situation is. But I thought it is very important that many of you have been asking questions about the various number systems and you are confused in those number systems. So I thought it may be a good idea to start with the number of digits or binary digits which are there in any kind of I think these are for the computer as well as any digital system. You will be finding these particular digits available over there. And we start with, on the left hand side is what we know, right? These are all the decimal numbers. So if we start with decimal 0, in binary it is going to be, and just 4-bit binary we are using. So 0 is going to be 4 zeros followed by 1, right? So that's why we are using 4-bit binary, because we have gone from 0 to 15 only. Okay. So, and that is what, this is 4 binaries, and you go from, if you see the decimal and binary conversion, so the 0, 1 is 1, right? 2 to 7 is, you can refer to this. Okay, 8, this is 1, 0, 0, 0, 2 to the power 0 is 1, 2 to the power 2 is, 2 to the power 1 is 2, 4 and 8, right? So this is 8 and rest is 0, you can refer to that. 9, now 9 in this particular case, now in binary, the 9, I think there is a mistake here, one extra 1 is there, right? So this you can correct yourself. 1001 is actually 9, and that has been corrected in the 10. 1010 happens to be 10. Very interesting case. 10 is 1010, but it is not called 1010. It is 1010, right? And 11 to 15. So this 1011 to 11111. All right. Now look into the equivalent BCD. So when we move from 9 to 10, okay, till 0 till 9. Everything is same, right? With this correction, right? Everything is same, all right? In the binary as well as BCD. But BCD is primarily, what is BCD? Binary coded decimal. Now in binary coded decimal, what is done? One decimal digit is represented by 4 bits. That's all. All right. So if I am referring to 10, so what 10 consists of? 2 decimal digits. So the representation for that binary coded decimal is going to be 1 becomes 0001, 4. Okay, so 2 digits are there. 1 digit is represented by 4 bits. All right, and this is 0. So now it starts from 0001 till 19 it will go, right? We have shown till 15 only, but it will go till 19 as 0001, 1001. And then 20 will become once again 0010 followed by 0000, like that. Okay, and 100 once again will become 1, 4 zeros. I mean 1 basically 0001, 4 zeros followed by another set of 4 zeros. So that is how one digit is represented with the help of exactly 4 binary digits. Okay, for 1 decimal digit we are referring to. All right. Now, if we move on to the hexadecimal, I think hexadecimal will be visible to you. It's only the octal which may not be visible to you. Okay, so hexadecimal 0, 1, 2 to 7, that's all right. Okay, they are referring over there. 8 is 8, 9 is 9. However, this 10, right, 10 in hexadecimal number, now digits are represented, there are 16 digits in hexadecimal notation. In binary we had 0 and 1 only, right? In decimal we have digits 0 to 9, but whereas in hexadecimal, likewise in hexadecimal we have digits from 0 to 15. F represents 15 actually. So F is 1110. So wherever calculations will be performed by us, we'll be using F as 1111 or 15. All right. So that is how you're going to use F. So B, likewise you can see B is going, A is not going to be this. A is 1010. Okay, so A is equal to 1010, which happens to be equivalent to 10 in decimal. But we have only single digit hexadecimal for that. Alright, so all the representations in binary are utilized in hexadecimal, whereas in BCD only 9, in fact 10. All 0 to 9 makes it 10 representations are only used, right? Remaining 6 are unused, which is that is going to be this A, B, C, D equivalent, that is 1010 till 1111. So they are unused over here. All right, and then there is another interesting representation which is called octal. Now hexadecimal is equal to 4 binary digits directly. BCD is equal to 4 binary digits, but BCD does not use all the combination, whereas hexadecimal use all the combinations. And octal is only 3 of these binary digits, right? So we will go, I mean, just leave the topmost 0 which I am showing you. Just don't think about the topmost 0 and it will become octal. 0, 1, then 0, 1, 0 is 2, like that, 2 to 7. And finally what you will get, this 1, 0, this becomes 1 and 0. This is 7, all right? 1, 1, 1 is 7. So forget about 0, in octal it is 2 to 7, then this becomes 10 in octal. 1, 0, not 10, 1, 0 in octal. All right, right. This is how the representations are. Octals are, we will be using, seldomly using octal representation, but you should know about them because at any point of time, anybody can use either hexadecimal or octal or BCD or binary, and that is why this particular slide is there to explain to you what exactly these things are and how they are equivalent. Very important once again to remember, one decimal digit, okay, is 4 BCD bits, all right, binary coded decimal, and 10 is represented as 8, right, because there are 2 decimal digits, so 10 is represented as that, whereas in hexadecimal 10 is going to be just A, all right. That will be 1010, 4 digits of binary only, right. So we go further then. All right. So first program which we will be doing is ASCII digits to packed BCD. All right. Now packed BCD is what? Now packed BCD, this is a packed BCD. Why? Because in 8 bits, how many decimal digits we are representing? 2. So this is how, this is a packed one. Packed in 8 bits, it is packed. All right. So this is what we are going to do. Now the data segment is very, very important here. Now what we want to do and how we want to do. First is ASCII digits to be packed to BCD. That means when I'm having memory locations, it should store the ASCII digits. Now how do I communicate to the assembler that this is ASCII digit? All right. And just not hexadecimal digit, right? So if I enclose it in quotes, right, single quote, it simply communicates to the compiler that it is an ASCII. And remember one particular thing, whenever you input anything, all right, you input anything from the keyboard, it is ASCII. It's some of you who may be web programmer, they know that you got to convert ASCII to digits, right? Digital conversion, where the entered, suppose you have entered 59, right? Then 59 actually goes an ASCII and it is to be converted into equivalent decimal or equivalent binary or whatever there are functions to do so, right? So all these things which you must, the basis is this. Basis is that ASCII is represented as single quotation over here. All right. Okay. Then this is also 9. This is ASCII. So high digit, basically what I want to inform is that I want 5 in the upper 4 bits and 9 in the lower 4 bits. That's what I want as far as my BCD is concerned. So instead of question mark, I want this particular value because my input is 59 and input has been stored into, in this particular case, some other program we are assuming has stored into memory location with 5 as ASCII and 9 as ASCII. Alright, and this is our BCD number which we want as the output of this particular conversion. Now, how the conversion is going to take place, that is very, very important. So, what I have here is 5 is 0011 followed by 0100. Now, this is very important. You can check ASCII table. Equivalent hexa you must check, not equivalent decimal value, equivalent hexadecimal, right? So, this hexadecimal, if you see, this is basically 3 and this is 5, alright. So, this a very important point about here ASCII, when ASCII designers were doing this particular problem, they were given this particular task, how to design code. So, what they made sure that the lower 4 bits are same as binary value of this particular digit. That means 5 is 0101, isn't it? But upper 4 bits may be different, but the lower 4 bits are this only. So, 9 is going to be 0011 same, but then this is 1001, equal to 9, right? Lower 4 bits are 9. So, technically this is a very interesting property. This is there. I mean, nobody has responsible for it, but the designers utilized the advantage of, I mean, they understood the advantage of doing this particular thing. Otherwise, ASCII to binary conversion would have been a very tedious task. With this particular thing, converting ASCII to binary is one of the easiest of tasks, right? So, that is what I just wanted to inform you. And now, what is our objective? I want to create 5 here and 9 here. Now, look into my requirement. Okay, they are very specific requirement. So, first of all, these 4 digits, okay, these 4 binary digits should be made 0 somehow in both the cases by using program, and then this should be shifted left 4 times. Alright, this should be shifted left, and then once it has been shifted left, this has been made 0, I simply OR them together. So, this is exactly what the program should look like. Okay, the code segment, and assume, I have already told to you that assume simply tells the assembler that code is the name of code segment, data is the name of data segment. You can create any name, nobody stops you from creating those names. Okay, and code segment register is loaded by the loader. Data segment register you have to load with the help of the first 2 statements. Move AX data, which moves the data segment first location address into AX register, which then is loaded into data segment register, right? So, initialize data segment using AX. That's what these 2 instructions will be doing. Then, now what we want to do, first of all, our digit, right? Our objective is to clear this particular information in 5 as well as in 9, both the cases, right? So, but to do that, we need to put them into the registers. We can't do this particular operation in memory. So, we brought the high into AL register, and this is a very important operation, AL with 0FH. Now, this operation is shown over here. As we brought digit high into AL, what did it contain? 0011, 0101. So, AL got that particular value, and now what you are doing? You are ANDing with 0F. 0F is a hexadecimal number, 0000 followed by all ones. F is 4 ones, right? Now, you do AND of these 2. So, 1 and 1 ANDed will be 1. 0 and 1 ANDed will be 0. 1 and 1 ANDed will be 1, and 0 and 1 will be ANDed 0. Can you notice one particular thing? ANDing with all ones will bring me the value of the other register, right? Whatever is the value of other register, that will get copied here. Okay, but ANDing with 0 will blank this particular portion out. So, that is the simple AND operation which we have utilized. Alright, so this AND operation will simply clear this 0011, and the result is now my AL register contains only digit 5, and it is unpacked because the higher digit I have the potential of keeping one more BCD digit over here, right? So that is what it is. It is slightly inefficient, but then I have converted AL into what I wanted. The digit 5 is over here and this has been blanked out. All right. Same thing we will, before we do that, then what we want now, what I told you, I want this 5 as the higher 4 bits, right? Because my output is going to be, my output is expected to be 5, right? If my output is expected to be 5, then I need to bring this particular value over here. Okay, to bring that particular value, I got to do the rotation. And rotation, by bringing in, first, how many times I have to rotate? I have to bring this whole thing. So, 1 rotation, 2nd rotation, 3rd and 4th. So, 4-bit rotations are required to happen, because 1-bit rotation, I'll tell you how exactly it happens, but then we move 4-bit CL with 4, the counter with the 4 value 4, and we rotate left AL by the value 4, which is CL, right? So, we rotate it by 4. Now, in the first rotation, how it is going to take place? Let's think. This 0 goes back. Rotate. You are rotating, right? You are rotating left. So, whole thing is getting rotated, right? And this 0 will go back and will sit over there. And this, everything will be moved over here. It is something like when you are taking turns, right? Onto a, let's say, slide, right? So, first person goes, right? He or she goes to the slide, and the second person becomes the first, right? And that person, after taking the slide, goes back to the back of the queue. So, if 8 person are standing there, so after 4 rotations, the 0, 1, 1, 0, 1 will be moved in this particular location. So, that's exactly what you can refer to any example of the life, and this is what the rotation is all about. Nothing very, rocket science or no big deal. I mean, this is simple, okay? Everything is simple. Only thing is you learn that particular logic and you will be able to do lots of things in assembly language programming. Okay, moving on to BL with digit low. So, now we are digit low. What digit low was? Digit low was 0011, ASCII 9, right? So, this is ASCII 9 which has been there now. Okay, it is moved, and once again with 0FH. Okay, so when we do that particular with 0FH, which happens to be this will be blanked out and 9 will appear as it is. Okay, 1 with 1, 1, 1, 1. You can try it out. It's very simple then. Okay, and now we have BL register with 0001, 10001, and AL register with 0100, 0101, and all 4 zeros over here. So, if we simply OR AL and BL, what will I get? Let me try from the right, this side, I mean the leftmost, that most significant digit, because probably you won't be able to see this particular area, or if you are seeing, it's perfect. But let's try to do it from here. 0 to 0 and 0 will become 0, but 1 and 0 will become 1. 0 and 0 will become 0, and 1 and 1 become 1. So, ORing with all zeros, what it is going to bring? It is going to bring the AL 4 bits here, directly copying. And ORing with all zeros is once again going to bring the result of 10101. You can try it out. I get the required result 59. Where exactly I wanted this 59 to be? I wanted this particular value in this particular location. So, I have to transfer it back. I got it in AL. Now, I just need to put it back. So, I move it to AL register, and this is the typical termination conditions which are essential using 21H. Last time also we discussed about it. This is called function 4C00H, which terminate. This is DOS function call. We call it DOS function call or interrupt 21H, which basically will take you normally, which will return directly to the what we say to the operating system. It will return the control to the operating system with the statement that everything is fine. The program has executed correctly. All right. So, this is how this particular program is going to work. All right. Now, let's move on to the next thing. Now, how to find larger of 2 numbers. Now, this is a very important topic, because most of the time without comparison, okay, without comparisons you cannot write programs. All right. So, use the instruction which we are recommending is CMP instruction, and the CMP instruction takes 2 operands. All right, and those 2 operands then are checked Now if AL is equivalent to BL, is same as BL, equal to BL, then zero flag will be 0. Why zero flag will be 0? Because compare will subtract AL and BL. Okay, so it subtracts the value and the result of the zero flag will be 0, because the result of this particular operation, it does not changes the value of AL or BL register, but it simply subtracts source from the destination. So what it is going to, this compare instruction will not change value of any register, but it is the last executing instruction. Therefore it will, whatever are the results, okay, whatever are the results in the whatever the significance of that, it is not going to move the values anywhere, but the result of the flag registers, whatever is the results, they will be setting the flag registers. They won't be changing AL. Okay, it's only will be changing the zero flag or whatever flag registers which are there, which are affected by it. Now if AL is less than BL, then the subtraction will require borrow. Therefore carry flag will become 1 in that particular case. Okay, so you will find that if AL is less than BL, the carry flag will be set to 1. If AL is greater than BL, then carry flag will become, now AL is greater than BL, so no carry is required and the zero flag is 0, right? So both will be not set. Okay, so this is how we recognize whether AL is equals to BL or AL is less than BL or AL is greater than BL. So that is the simple form of instruction, and how we use it, that makes the things very, very interesting. So adding a value in an array, that's what we are programming. Now these the values which have been shown over here, they are assumed to be BCD. Now once again I am trying to tell you, last time also I told you, whatever values are there, right, it is I who determine what my program is supposed to do. So it is I who know that this is BCD or it is hexadecimal or it is just ASCII value. All the values can be in hexadecimal, ASCII or whatever, they can be in hexadecimal. Binary equivalent is always there. ASCII has binary equivalent, just like I showed you 0011 and followed by 0101 is the value of 5, right? So this 36 can be, this 36 can be equivalent to, technically speaking, ASCII 6. Right, but then it can be hex digits also, right? The binary value also 36 as binary value, which is different from BCD value 36, right? You remember BCD value 36, the 10 we required 2 digits, 4 binary digit pair, right? Whereas 10 was just A in hexadecimal notation, right? So all these values you determine. Okay, so that is why I brought that particular slide to you, and please read that particular slide very meticulously. Try to understand it. If you do not understand, ask questions. There is absolutely no problem on asking questions. We have a group MCS 012 where you can ask questions about whatever you have not understood. Alright, ask questions so that we can reply to you. But please don't ask questions related to assignments. That is what we discourage. Okay, assignments, you take the pleasure of solving assignments. Okay, that pleasure, nobody should take away from you. So you should try to solve your assignment yourself. Although you can ask related questions, not exactly what is discussed in the assignment. The conceptual stuff we will tell you. Right, but we will not tell you how to solve the assignment question problem. Okay, try it yourself. It is one of the, you see, if I don't face a problem myself, right, I'm already defeated by the problem. So how you are going to learn? Your objective is in IGNOU. You have come to IGNOU to learn, to get a job, ultimately to become better from wherever you are. You want to become better and try to get a job, and that is what you should try. Okay, so that is what, everybody will advise you like that, but you are the best judge of what you want, but then this is what is going to take you higher in your life, and that should be recommended by you to yourself. Nobody else can recommend it to you, right? Do assignment by yourself. Do all the practical questions which we have asked you yourself. You take help at any point of time. You are struggling, take help, right? But that is learn about it and solve the problems. That's it. Okay. I mean, enough sermon of that kind. I mean, you know, you are better persons than most around here. You are there to learn, so we know you can do what you can do much better than many of us what we can do. All right. So now let's look into the arrays. So now in this particular case, the name has been prices DB 36H is what I'm saying. Once again, I'm repeating, this is binary coded decimal value, right? So this is 36 in decimal in one particular sense, and there are, you can see 1, 2, 3, 4, 5, 6, 7 and 8 values there. So we have to process this 8 value. So somewhere down the line we know the counter, wherever the count, we have to process 8 values. All right. So what we have to do, add a value in an array. So in every value I need to add a value and write it back. So I read this value, add some value into it and write it back. I read this value, add, write it back. So one by one, I think we can't do all, adding value in all the values together. We need to read them one by one, all right, and put it back. All right. So that is how we need to do the operation. Okay. So obviously, when we want to do same operation for a number of values, then I need to do the loop. All right. Now we will do loop two ways. One by using loop instruction and one by very elementary methods, that what we are supposed to do in assembly technically, and how 8086 simplifies it for us. All right. So this array is the name of data segment, okay, and price is the name of or the offset of the first location 36H. All right. Then we assume, now you remember this DS in node data segment is actually, the name of data segment is arrays. That's why it is there. All right. Then you move initialize data segment over here. I have nothing to make any more statement about it. So this is what it is, and these are the termination statement. The in between program, let's talk about that, right? So this is the basic shell of the program, where the data segment is there and all these statements are going to be everywhere, right? So I mean, you don't need to, what we say, you don't need to remember these statements all the time. When you write program, you yourself will start remembering them, just like mathematical formulas. When you start using them, you remember them by heart, right? So these are some of the statements which you remember by heart because you know the logic now. I have to start with the data segment, then I have to tell to the compiler that this is the code segment, this is the data segment. Since data segment is not initialized, I need to initialize it and I need to terminate. Right, and I need to terminate as well as tell to the assembler that okay, the whole code is over, my code is over, and this start symbol should be terminated. So my whole code is over, and you can now start doing the linking, loading, and other assembling kind of a thing, so that you can convert it into assembly program which is runnable. Right. So these are very standard statements. What changes is this. Okay, so adding a value in an array. So I have shown you with the help of few registers. There will be slight, once again you will be finding some values cannot be seen, but then we'll be discussing about it and you will come to know about it. Okay, all right. So first statement is very important. Now this prices that once again you can see the spelling, it should be prices over there also in the data segment. That's a simple thing which you can understand. So what we are saying, load effective address. Okay, this is the statement. The prices, the address of the location prices has been stored into BX register. What does it mean? This prices, I'm just shown this particular thing over here. You can see I have given a random address 1AFE, right? And this is 16 bits. 1AFE is a hexadecimal, so it is 16 bits, right? 2 to the power 16 is what we said, 64K segment, right? So this is how. So any address, so prices is 1AFE. So the next location is going to be, this is byte, right? These were the byte values, 36H, 55H, right? These were the values, right? 55, 27, right? You can see here 27, likewise. And the last is going to be 39. Each one at the next location, 1A FE. What is the next location? If I add 1 to E, what it becomes? E is 14. I add 1 to it, it becomes 15. 15 is F. So 1A FF, that is what it is. I add 1 to it, what it becomes? F plus 1, 16. 16 means it is 0 and carry is 1, right? So 16 is 0, carry is 1. F plus 1 is once again 16. 16 means what? The digit is 0 and carry is 1. So if I add 1 to A plus 1 is, A is 0, the 10 value, decimal 10, 10 plus 1, 11. 11 is B digit, B hexadecimal digit, and 1 remains like it. So like that it has been incremented. I just wanted to show this, that's why I assumed. Alright, so then we add B1, then 2, then 3, then 4, and finally the 5. So that is how we will be having the locations. Now effective address, what is the effective address of BX, the prices location? 1AFE. So what is going to be the result? The BX register will be loaded with 1AFE in hexadecimal. And what does that location contains? 36H. So the first statement, load effective address, will load BX register with this particular value. Alright. Next, I am moving CX with 8. Why 8? Because we have 8 values. Remember? Okay. So this counter register is the one which is going to take care of how many times the loop is going to take place. And do next is a label, because this is where we are saying jump back to do next. Alright, so go back to this location. So in a sense we are looping here. Alright, so this is the looping construct which we are trying to implement. What have we done over here? Move AL comma the content which is pointed to by BX register, indirect addressing. BX was pointing to 1AFE, right? So move into AL whatever is pointed to by BX register. BX is register pointing to this particular location initially. So 36 will get loaded into AL register. That is what you get here. Alright. Now in this 36, what are we adding? 0AH, that is 10. We actually should have stated 10, okay, but that's alright. 0, because we are referring to them as BCDs, right? So 0AH, when we add into it, we actually get this A plus 1 is, A is 10, 10 plus 6 is 16, right? So we get 0 followed by 3 plus 1, 4. Now this is actually incorrect. If I add 10 to it, I should get 46 as far as BCD is concerned. And that conversion from 40H to BCD is directly done by decimal adjust after instruction. This instruction has been designed that whatever is the content of the previous edition, it is adjusted with next decimal or into a BCD value. Fortunately, we don't have to go into the detail of this particular instruction. It does the job for us. Alright, if we have to implement that instruction, we will have to write a major program for it. So what we are basically saying, it will be changing it to 46 for us, and that is what we wanted in that particular scenario. So believe me, in that particular sense. Otherwise, you can try it out onto the assembler. Alright. Then move, so technically that is why I am saying let it be 10H, the program will even better. I mean from the understanding point of view, because then it is perfectly BCD. Alright, so move BX AL. So what we are doing, BX AL, that means BX is still pointing to 1AFEH, right? So BX is still pointing to it. The value now, whatever has been after the decimal adjust, which we should get as 46H, should be written back to that particular location. So now the location will be written as, I think this is where you can, I have written 40H without thinking about DAA, but you should you can try it out using compilers and assemblers. It should be actually 46H. Likewise, all these values. Alright? Okay. Then what next we are doing? Increment BX. Now remember, over here when we are saying in bracket BX, whatever is pointed to by BX. Now when I increment BX, what I am telling to the compiler, or what instruction I am executing, I am telling that now move from this location to this location, right? I have added 1 to it. All right, Bx contain 1a Fe, right? Now when I said increment Bx, I made it increment by 1, which is 1a Ff, and now it contains 55H, right? So like that. So next this will be, okay, so Px is now pointing to the second location. Okay, decrement Cx. Why decrement Cx? Because one instruction has, or one of the 8 array values has been already been executed. I mean, already has been performed. Whatever task we wanted to do with one value, that has already been performed by us. So decrement the value of Cx. Now while decrementing, if this becomes 0, right? Suppose Cx becomes, now in the first case, because it was 8, so it will become 7, right? It will become 7. In the case when it becomes 7, what we are going to do? 7 is not 0, so jump not 0. If 0 flag is not set, go next. So it will keep on doing this particular thing. So for 7 it will do, then for 6 where the address will change in the increment, decrement will once again decrement it, and the whole process will get repeated for 1a Fe, then 1a Ff, then 1b00, then 1b01, like that till 1b05. For the last one, when this particular operation is performed, that is the time when you increment Cx. Cx is decrementing all the time, right? So that is the time Cx will become 0 and the loop will terminate. Okay, now the loop will terminate means it will go to the next statement over here. Alright, so that is how the loop is going to terminate. Now another example which is there is when we are printing off alphabets from A to Z. Now this is another example where I said the loop condition. So what we require in loop? We required in loop decrementing of Cx and checking if there was a jump instruction, not 0, J and Z, right? So that is J and Z instruction, 2 instructions we require. Now both these instructions by 8086 designer has been put into one instruction called loop. So loop takes care of decrementing Cx and also checking whether the result of decrementing Cx is 0 or not. Right. So this particular loop instruction will be consisting of 2 statements. Alright. So now what we are doing in this particular program, let us very quickly do this particular program. Okay. Now AH with 0 to H, when it calls interrupt 21H, which happens to be taking place over here. Alright. Main P, etc. This is what I'll just explain to you. But this particular interrupt outputs whatever is the content of DL register. Now DL register contains one alphabet. 41 represents A. Alright, 42 represents B. Like that, A, B, C, D are contiguous in this particular sequence, and that is why this program is going to work. So what we are going to do, now I want to print alphabet A to Z. So first the A equivalent ASCII value is to be put into DL register and I want to print it. Okay, so this statement, so rest everything is fine. Move Cx 1AH. 1AH happens to be 26, right? So 26 alphabet. So Cx is initialized with the value 26. Then the first, that is A, is moved. 41 is actually ASCII equivalent of A, capital A, right? Small a is going to be different. So capital A is moved into DL register. I think we could have simply put A, capital A in 2 quotes. That would have done the same thing. Okay, then this is where the loop is starting. Move AH0 to H, 21H. So what it is going to do, whatever is the content of DL, which happens to be capital A, will be shown onto the screen. Then increment DL, and increment DL, after that what we are using? Loop instruction. What does loop instruction do? Decrement Cx, and if not 0, it will take you back to next C, which happens to be the label for this particular instruction, right? So you basically are looping here, and once all the alphabets are printed, you terminate this particular program. So this is how you're printing through loop. Basically loop. So what we have done, 2 concepts. AH with 0 to H in the AH register. Okay, this is a call this is a interrupt 21H call, which is going to with the function 0 to H, which outputs the value whatever is stored in DL register. And DL 41H is not 2 digits. It is only single ASCII digit and it is equivalent to A in this particular case, then it will be B when we increment it, right? Every time we are incrementing DL, right? Still it will go to Z, and 26 is going to be controlled. 26 time loop is going to be controlled by loop statement, which will decrement CX all the time and checking if the result of decrementing is 0 or not, right? So this is the way it works. Now finding the smallest and largest. Now this is another interesting program which you will find. Now over here there is a slight change. Data word has been used instead of data byte. Alright, so now you will find if it is -1, it is going to be stored in the form of 2's complement notation. 2000, okay, now all these is going to be in the 2's complement notation. They will be converted and stored. Large is a value where largest of the value will be stored, and small is the value where smallest value is going to be stored. So this is what is my data segment, and these two instructions are very standard, so no discussion about them. Now let us discuss about these are data words. So now look into the addresses 1AFE. From 1AFE, what is the next one? We added 2 into it, E plus 2, F and 0. So we get 1B00. Added 2, added 2, added 2, added 2. So this is how these values are going to be, and these are their binary equivalent. Right now binary equivalent are not that important. What is important here is how this program is going to execute and what the results we are going to get. So first we move into in the array, that is the first location, into DI register. All right, and what we are, so DI register is what, which is the index register we have not shown. So DI register will store first this, then this, then this, will keep on incrementing. So remember, somewhere down the line DI is going to be incremented, which may not be here. Onto the next page you will find DI will be incremented by 2, and DI is being used as a pointer register to these locations, right? All right, so then move DXAX. So what we have done, the first value has been moved to AX register, which is -1. Now it has been moved to DX register. So now what, DX stores the largest and BX stores the smallest. So both the values are now set to -1. All right, and since we have 6 values, so we can start with CX value 6, and then we are moving in this case we are moving the first value just to demonstrate, but we can always start from the second value. For that we need to increment DI by 2 and then start, but it's all right. All right, okay, so we moved DI. So we'll start with the second value only in this particular case, and assuming that one step has already been done. Now what happens when we move DI into AX register, right, and compare AX with BX? So what is BX? You are comparing with the smallest value. All right, when you are comparing it with the smallest value, okay, what is the value in the this second time? What do we get? 2000. 2000 is more, right? So jump greater than equals to. If it is greater than or equals to, go to another place where right, mean it is more than the jump greater than equals to. Why? It is more than the smallest, but is it the largest? Okay, that is what we need to check. So then we are taking it to another label where we will check whether it is the largest or not. Okay, if it is not the largest, we simply ignore it. Okay, if it is greater than, if it is not, if it is jump greater than equals to A2, we go to somewhere else where we will be checking whether it is largest or not, because it is more than the smallest. All right, so right now it is more than the smallest, so we'll go to A2, but right now we are not going. But suppose it is not smaller, if that jump does not take place, then what we are going to do, that means whatever is the value in the AX register, right, is smaller than BX. Okay, and that is okay, we'll come back to that in that particular case. Okay, so we take jump to A2 register. So we jump to A2 register, and what happens? AX is compared with DX, which is the largest value, which was -1, right? 2000 is greater than -1. All right, so jump less than equals to A3. No, it is false. So this jump is not going to take place to A3. So what is going to happen? Move DX AX. That means in DX register, AX value will be moved. That means it becomes 2000. So now the value has changed to -1 2000. All right, then add di with 2, okay, loop to a1. So automatic decrement. Now loop is going to take care of decrementation by by 1, right? Decrementation of CX register, and then move large loop to a1. So once we go to loop to a1, and if CX is 0, then we go to the next statement, but it is not so. So where we go back? We go back to our this statement. Now what we have read is minus 4000. Now minus 4000 is less than minus 1. So what is going to happen here? Okay, now over here comparison is taking place between AX and BX, alright, and minus 4000 is smaller. Minus 4000 turns out to be smaller, so this jump is not going to take place. Alright, so just this jump is not going to take place. When this jump does not take place, move BX with AX, right? So what is going to happen? Minus 4000 has been moved to the smallest value. Alright, so minus 4000 moves to this particular value, and now you jump to A3 to take the loop. Loop actually is executed over here where DI is incremented and you loop back to A1. Alright, so if CX is 0 or not, that is what we are checking over here. If CX is 0 or not, if CX is not 0, go back to A1. So likewise, now minus 4000 has come over here. So what you will find, another 32767, which happens to be the largest, will also it will find place, and similarly the way I have shown to you. Now the important thing is about 500. Now in the case of 500, what happens? Now 500, when we compare at this point of time, right? So we have these two values. So when we compare 500, now BX is having this particular value, AX with BX. AX is what? 500. Now 500 is not less than this. So what is going to happen? Jump is going to take place to A2. Jump has taken place to A2. Is it less? It is then it is less than AX and DX we compare. Now it is less than 500 is less than this. So jump is going to take to A3. So no changes there in these two values now. Okay. Similarly, it will happen for 0. So for both the places, this is what is going to happen. And once all the values has been, the loop CX value becomes 0, that is the time when this loop will terminate and next statement will be executed, which will move DX to the large value and small BX to the smallest value, and this is how the termination is going to take place. So this is, in general, this is how you can do the operations as far as assembly language programming is concerned. There are many more programs which are given in your blog. You can refer to those programs. One more program which I have demonstrated over here with the help of example, you can study for yourself first. Okay, it tries to explain all the details, like how exactly it does the basics, like how the values are going to change for the given values. Okay, and this is a very important and interesting kind of a situation. Learn it in this particular context. Try to solve the problem. Okay, in the given way. Okay, the way I have tried. I mean, go through along with the problem. How exactly this step is going to take place, this step is going to execute, how the value of AX and BX is going to change. Now, while solving this particular problem, you will be learning assembly programming for yourself, and then go on to solve your other problems which may not be in your block. Alright, so this is how the learning of assembly language programming is going to be very, very effective, and you will be able to do lots of things. There are few questions which are there in the check your progress. Okay, so you can try it, do your previous year question papers, you can solve those type of problems. Okay, then there are a number of practical sessions on this, so you can solve the practical problems also on paper. No need to go to an assembler. First solve it on paper. Do a typical study with it by using, okay, how it is going to change register, how values of various variables are going to change. That way, if you do the brass tracks or situation, then you will be able to deal with assembly language programming in a very simple way, right? So just remember that loop is very, very important. Jump in assembly, all right, the conditional checks we use. By conditional check, they set the flag, and those flags are used in the, for example, jump greater than equals to statement, or there was another statement, jump less than equals to. All right, so these statements use the flag which has been set by the CMP instructions, and on that basis whether this jump is going to be take place or not, that is determined. If jump is not going to take place, then the next instruction is followed. If jumps takes place, this instruction will be skipped. Right, so we'll move directly to over here, and loop is always going to take us back to a particular place if Cx value has not become 0. As soon as Cx value becomes 0, this loop will terminate and we go to the next statement after this. So this is how an assembly program works. This is how you can write your own assembly programs, and this particular program, if in just 1 minute if I can tell you, this 1000 equals is another directive, assembler directive, which basically puts 1000 into a value, and the objective is, this is a data word 4567 tagged. This is BCD, we have assumed them as BCD, so 4567 is tagged BCD. The objective is to convert it into equivalent binary value. Now to convert it into binary value, a very interesting stuff is done, because all operations are done in binary. So I multiply 4 with binary equivalent of 1000, I multiply 5 with binary equivalent of 100, I multiply 6 with binary equivalent of 10, and I multiply 7 with just 1, so I simply add 7 into it and I'll get all my results. Alright, this is exactly what has been done in the program. It has tried to tell you. The rotation has also been explained in the similar way. Rotation is by 4, so you can make it out. First step is to basically separate the bits. Okay, we have 4, 5, 6, 7. So separate them into AH, AL register. Then in AH register you bring 4, okay, by rotation, right? So bring 4 into AH, bring 5 into AL, bring 6 into BH, and bring 7 into BL. So this is how. So break this 4, 5, 6, 7 into different registers, each as unpacked BCD. And then with each unpacked BCD, you multiply the value. For example, AL into DI into 1000. So we have multiplying DI. Now look into the multiplication register instruction. It is explained here how it is done. When you multiplication takes place between AX and DI, because it is a it is a word operand. So the result is going to be 16 into 16, 32 bits. Alright, so AX into DI result is going to be here like that. So all these then will be converted into binary. Somewhere 7 will be added, then 100 will be multiplied. This is 64H, right? Then this is how everything has been explained. So you must refer to this particular slide. Alright, download it, refer to it, and apply to other places also. So that is how you learn assembly programming. Whatever programs are known to you, whatever programs has been explained to you, learn them by heart. Like what exactly this program is trying to do. Learn those instructions and then use these instructions and addressing modes to write your own programs and enjoy it. Thank you so much. Bye for now.